Hi everyone, welcome to Lab 2 for ELEC 2507. My name's Adam again, and today we're going to walk you through what to do here. So I'm assuming you've already done your pre-lab calculations. Your pre-lab is very important for this lab because if you don't do it, you're going to have the wrong resistor values for all your differentiator, integrator, high-pass, and low-pass circuits. Also, make sure that you're going to the resistors.pdf file downloaded from CUlearn. And from there, you'll find everyone's resistance value for R1, R2, for the inverting op amp, and the summing op amp. Use these two values. So make sure you find your assigned station number, and then look up your assigned resistance value, and from there, you'll be able to do your pre-lab calculations for number 1 and 2. So once that's all done, you can go ahead and log into CUlearn. Go ahead, scroll down, and find the Lab 2 section. Once you're there, you'll see a folder called the Lab 2 Multisim files. And you can go ahead and download the folder, or you can just go ahead and download that individual file, whatever you'd like more. Please keep in mind that this is all done on the remote connection that you guys previously accessed in the last lab. So you're doing the same sort of procedure. Go find your station number in the odd even subgroupings list. Go to the lab stats page and log in to that particular station only. Okay? I had some station students logging into the station that I posted in the video, and that's not correct because I just used the first station in the video, and you may be assigned the second, third, fourth, fifth, etc. Alright, once that file is downloaded and you're ready to go, so go ahead and open up that file. I already have. And as you can see here, it gives us a schematic with every circuit that we're going to perform in this lab, and it has them all labeled 3.1 through 3.6. Okay, and if you go back into the Word document, you will see that there is every section 3.1 through 3.6 that is done in software, and then 4.0 will be done in hardware. So the first step it asks of us is to get a 100K resistor and one resistor of value R1 given by your lab station number in resistors.pdf. So you can go ahead here, find the circuit for 3.1, which is right here, and you can go ahead and click on the particular values you need to change. So in my case, it's asking for RF to be 100K, and it's asking for R1. My case is only 5K. So I'm going to put 5K here. So if I was assigned station number 4 in this case, I'd be using an R1 value of 13.2 kiloohms. If I was assigned station 11 per se, I would be using a value of 33 kiloohms, and that is given by resistors.pdf. All your op amps are already powered for you, so we already have the connections here for negative 15 volts and positive 15 volts on every one of the op amps. So they all should be powered. You shouldn't have to actually remove or replace any of those connections. So the very first step asks us to actually connect the amplifier, which is already done for us, and use the RF and R1 resistance value given by your lab station number, so I've already updated that. Now we're going to calculate the expected gain using the tolerances on the resistors. So how will we go about this? So there's a 5% tolerance on this resistor, and there's a 5% tolerance on this resistor, right? So we know that maximum gain actually happens when this resistor is very large and this resistor is very small, right? So if we do the minus 5% of R4 and the plus 5% of R3, we'll have an upper bounds for the gain. If we do the negative 5% of 100K and then the positive 5% of R4, we will have the minimum bounds for the gain. So you can go ahead and calculate those and see what they'll be, because your gain that you get out of this circuit has to be within those bounds, right? It has to be within the plus or minus 5% tolerances, and therefore by doing those calculations you'll find a range which your gain could be within. The second step it wants us to do here is actually connect the meter, the multimeter, and actually check the levels of the 15 volt supplies. So let's go ahead and we'll connect the multimeter up. The multimeter can be found in the top right here. If you go to the top right of your screen, you click on multimeter, you'll see it drag into the page. So go ahead and just drag it actually down to the very bottom here, because this is where our power delivery system is for this circuit. So we'll go ahead and just wire these up, just like so. So the negative terminal, goes to the 0 volts. Positive terminal goes to the top of the 15 volts. So once you have that connected, you can go ahead and run the simulation once more. And you can check the DC voltage. And you can see it's exactly 15 volts. Now that that's verified, we can pretty much neglect the negative 15 volts, as this is a simulation and we know it should be connected pretty much the same in an identical fashion. The third step asks us to apply a 1 kilohertz, 0.5 volts peak-to-peak sinusoidal signal at the circuit's input, and use the second channel on the scope to observe the output voltage. So what is the gain of this circuit? And we're going to compare that to our expected value. So let's go back to Multisim once more. And we'll go up to circuit 3.1. Oh yeah, by the way, if you guys ever need to zoom in or zoom out of this graph here, you can simply use your scroll wheel on your mouse. Don't actually press any control or anything. Yeah, just a helpful tip. So now that I have my resistor values set, I verified my 15 volt supplies and all that sort of stuff, I'm going to go ahead and this should already be set for you to a 0.25 volts peak, right? Which is a 0.5 volts peak to peak output or input waveform. And it's sinusoidal. So we're going to go ahead and run that. And once we've run that, we can go here and we see the scopes for both plots 3.1 and 3.2. So we can go in here, and from here, we can either hit normal, which will give us a continuously running waveform, or we could hit single, which will just stop the waveform for us nicely so we can take some measurements. And if you actually look at the colors of the nodes here, it represents the colors of the waveforms on your actual oscilloscope. So in this case, I have my V out set to black. Of course, black's not going to show up on a black background, so they've set it to white for me. But V in is my red, right? So I can go ahead and drag cursors, one at one peak and the other at a minimum, let's say, something like that, right? And I can see that my channel A, which is my input, right, is 491.459 millivolts, which is exactly, pretty much 0.5 volts peak to peak, right? And then if I go ahead and put the same cursors, but put them on my white waveform, and in a good way, because the cursors are currently on my red waveform, you could go here and instead of just visually inspecting where that actual marker is, you could go right click and click on select a trace. From there, you can actually click on what channel your traces are actually flowing through. So I'm going to click on channel B because I'm looking for my output, right? And from there, you can see now my cursors are placed on channel B. So I can put one at the minima and 1 at the maxima. Oh, sometimes it'll do that. It'll shift it for you. But once I have that, I can see that I'm around 9.959 volts. So from there, I can go ahead and calculate my voltage gain, or I could just simply go into the boat plot, right? Boat plot functionality will give us the same stuff. So we can go ahead and look at the magnitude as a function of time, as a function of frequency. So the magnitude as a function of frequency, it looks like it changes. I have a corner frequency at around 40 kilohertz, let's say, around there. My 3dB point looks like it's around 40 kilohertz. And my passband gain is around 26.02 dB. So you could go ahead and convert that back into volts per volt if you wanted to, just using the inverse of the 20 log of that number. And like you're asked to, you can go ahead and compare that to the expected value. And go ahead and take a screenshot of that plot for your report. So this part's a little different. In a real loud environment, you could constantly kind of change the value of this function generator, but we don't have that luxury in this case. So what we're going to have to do is continually just keep setting a different value until we observe some clipping in the output waveform, which is the red waveform, which is the white waveform. So let's go ahead and go back to our circuit, and we'll set it here to, let's say, 2 volts peak. So if we go back, hit normal, should see that that waveform is way too big right now. So we'll go ahead, make it a little smaller. So we can see at around 10 volts per division now we have a steady waveform, and we can see that it's already clipping, right? That clipping is just the flat tops and flat bottoms on the waveform. So let's go ahead and stop the simulation once more. And we can now lower that, right? Just to see where the clipping actually starts. So we'll go down to 1.5 volts, which is a 3 volt peak to peak. Go ahead and hit run once more. We can see it's still clipping, right? I'll go ahead and stop that. I'll put 1 volt in here. And we can see we're still clipping. Go ahead and rerun that. And we can see that the clipping is just starting at around 0.7 volts peak. So that's a 1.5 volt peak to peak for my particular amplifier here. And then I could note that value down in the lab book as the value where the amplifier is starting to saturate, okay? It also wants you to note the peak-to-peak voltage of the clipped output waveform. So we'll go back ahead and actually put our trace on channel B, which I believe it already is. Yes, it already is. So we'll make sure it's on channel B, and then we can measure the actual peak-to-peak here. So we can see peak-to-peak is around 28 volts. So when my output is around 28 volts, I know that I'm starting to clip and saturate that amplifier. Now after that's done, we'll move along to 3.2, which is the summing amplifier. So once again, you're going to go to find your R1 and your R2 value are given in resistors.pdf, okay? So you look for your sign station number, look for your R1 and R2 value, and then you're going to use them in this circuit, okay? So in my case, I had 5 as value of R1, and I'm also going to use 50 as my value of R2. So I'll go back in here. My value of R2 is 50K. and this value is 5K. So this value is your RF value, it's kept constant, and I can see my input waveform is actually in lime green this time, and my output waveform is in purple this time, okay? So I can go ahead and actually go back to the same scope that I was just on. And what I'm gonna do here is actually null the last circuit. So currently you're looking at the output waveforms of the last circuit, but what I can do here is switch to channels A and B using this particular roundabout thing that I don't like, and pressing the 0 function. Once you press the 0 function, next time that waveform pops up, it will be zeroed out. So that's what I currently have in place for channels D and C. So we can go ahead and actually just switch those to DC coupling for channels D and C. Once those resistance values are changed and you've made the changes necessary in the scope settings in XSC1 up here, you can go ahead and rerun the simulation once more. Then you should see a purple and a green waveform pop up, right? Purple is your Vout2, right, which is the output of the summing amplifier. Vin2 is the input to the summing amplifier. And we can see that the input to the summing amplifier is on channel C, and the output of the summing amplifier is on channel D from this scope up here, okay? So when you first open up the scope, you'll see that the purple waveform looks like it's way out of bounds here, right? And that's because the channel's DC coupled, right? And you have a DC input coming in here, and it is also getting amplified, right? So you could think of the summing amplifier as having two individual gain cases, right? So the first is the 0.5 volts DC that's coming in here and getting amplified by 100 divided by 50, right? And then the AC portion is the 0.25 volts peak, which is a 0.5 volts peak to peak, getting amplified by 100 divided by 5, in my case, right? So if the DC portion of the output is getting amplified by a factor of 2 here, right? That would mean, -2 actually it would be. Then that would mean the center of the output waveform should be technically at -1 volt, right? The center of that waveform. And in this case, the output's the only really thing we care about, because we just care about the superposition of the two waves, right? So let's go ahead and nullify the green channel. So go ahead and hit 0 there. Oh, sorry. And then go back to the D channel. And then you can see that it would take 1 volt to actually have that wave centered in the middle of the screen, right? And that makes sense, right? Because I have 0.5 volts going in here. So we can see the gain is virtually the exact same as the inverting op amp, right? 9 volts, and I'm putting in the exact same input. But the DC level is the only thing that's shifted here, and that's due to this DC input here. So you can go ahead and draw that in your lab book of what would happen when the 0.5 volts input gets amplified by whatever combination of resistors you have here. Next, we're going to increase the input once again, and we're going to view where the waveform starts to clip. So let's go ahead and just set it back to just a little over what we had last time as our final value. Our clipping range will be a lot smaller in this case because we're putting in a DC input. So let's go back down to like 0.6.
rerun the simulation. If you don't rerun it every time, your waveform's just going to look the exact same. So 0.6 looks like it's not clipping there. Go to 0.7. And we can see it's clipping on the bottom. So I'd say that would be a fine measurement to take. We could even go back to 0.75 and say that it's probably around the exact same value. Yeah, so only the bottom is clipping there, but that's still fine. That's when clipping is starting to happen and you're entering the saturation region. So 3.3, the differentiator circuit, asks us to connect the circuit as shown in figure 6 with the following values. So CI equals 0.1 microfarad and RF equals 10K. So let's go ahead and look at that circuit to verify it's what we have in Multisim. It looks like it is, right? And we have a 0.1 microfarad and a 10K resistor. Let's just verify that's what it asks us to do. 0.1 and 10K. Yep. So in this case, it wants us to use the signal generator. So the signal generator is actually already plopped down into the schematic for you. So you can go ahead and just delete that block for now. Once you've deleted that block, you can go ahead and wire everything up. So what I'm going to do is do Control-Shift-W, go from the positive terminal of the function generator to there. I'm going to go from the negative terminal of the function generator to ground, right? So once that's actually connected, like so, I can go back to the document and ask, so it's asking for a 1 kilohertz 0.5 volt peak-to-peak sine wave. So we want a 1 kilohertz, which is 1,000 hertz, right? And we want it to be 0.25 volts peak, right? Which is a 0.25 volt peak to peak. So once that's set, go ahead and exit that. And you can go ahead and rerun the simulation once more. Go into the scope for 3.3. And once there, you'll see a white waveform and a red waveform, just like in the first exercise. You can go ahead and blow up both those channels a little bit, make them a little bit easier to view. And something else I always like to do is hit single, just so I can get a constant waveform on my screen. So it asks you to sketch the input and output waveform as they appear together. And then increase the input frequency to 2 kilohertz. So we can go ahead and stop that. And actually switch this to 2000. Right? Once there, go ahead and rerun the simulation. And you're going to have to scale down channel B. So once channel B is scaled down, you can once again sketch the input and output signals and record the peak-to-peak levels between the two waveforms and explain the differences in the signals. So basically what we're looking here is for the phase difference between the two signals, right? So you're looking at how far in the x-axis in time is the one peak of the red waveform offset from the peak of the white waveform, right? And the way to do that is just by placing the markers just like so. I know it doesn't necessarily look very great, but the markers will do a good job for you of taking the subtraction of time here. And then from there you can calculate the phase angle between the two waveforms. So the last step in this portion asks us to change it back to a 1 kilohertz signal, so let's go ahead and do that. The other way you could actually do this, which may make it, well, will make it much easier, is just by going to the bow plot functionality, right, and looking at the phase, right, as a function of frequency, and then looking for the frequencies of interest that we're interested in. So we're interested in 1 kilohertz, right? We're interested in 1 kilohertz, and we're also interested, so we see there's a 90-degree phase shift between the two waveforms at 1 kilohertz, and we can see at 2 kilohertz we pretty much have the exact same 90-degree phase shift, right? And that 90-degree phase shift is due to this non-passive element right here, the capacitor, which stores and inducts charge. So the last step is to return to the input signal generator and switch it to a 1 kilohertz triangular waveform. So we can go ahead, open up that function generator once again, switch, triangular is this sawtooth kind of wave here, and switch this to 1000 hertz, which is 1 kilohertz once again. Go ahead and exit that and rerun that simulation. You hit normal, and then you hit single once again, just to get it. So we can see there's some ringing in here, right? But basically what's happening is channel A is our input, right? So this is the sawtooth triangular wave at 1 kilohertz. We can actually switch that back down to 1 millisecond per division. And this output here is basically, I know it doesn't necessarily look very much like it, but it is. This is the basic functionality of a square wave, right? There's some ringing in the peaks where the capacitor hasn't leveled out yet, right, in its particular charge value. So that's why you actually have those peaks and troughs. But if you look at the general shape of this, so follow the general shape, so follow the peaks and the troughs of all the waves, and you'll actually see that you have a square wave here. So that's what it's asking you to draw. Just draw those peaks and those troughs, or again, just take a screenshot of this and include it in your report, but maybe mark up that line, because you can see there's a line that's flowing along these kind of sinusoidal patterns here that makes up a square wave, okay? And this is called Fourier transform. This is higher level mathematics that you guys will figure out in 3rd and 4th years, but yeah.
So from there, the next step asks us to design a high-pass filter. So we've designed this high-pass filter in our pre-lab. The CI value that you're given is 0.01 microfarad. 3 dB cutoff is 3 kilohertz times 2 pi, right, which is your angular frequency. So we can find our 3 dB cutoff frequency using this formula, and we can find a value for Ri. We also know that we want the real part of this equation, so negative RF divided by Ri divided by 1, to be 1 in the passband, right? So we can come up with an equation that's simply RF divided by Ri, and then you have to take the source impedance into account, and then set that equal to 1, and you'll find that RF should just about equal the value of Ri. So in my case, I found a value of 318K for a passband frequency, a 3 dB cutoff, sorry, of 5 kilohertz is what I used for mine, okay? And I found that my Ri should equal my RF value, and those should both be 318.31 kilo ohms. So I'm going to go ahead and go back to Multisim, and then I'll go ahead and stop the previous simulation, and I'll go ahead and find 3.4. So the first thing I can do is make sure that my function generator is hooked up correctly. So if it's not, I'm going to go ahead and wire it. In your case, I've most likely already done this for you, so you won't have to worry about it, but it's worthwhile knowing how to do it. So once my circuit for 3.4 is hooked up, I can go ahead and actually put in my values for RF and RI. So I had 318.319. So I'll just put in 0.31K, right? 31K. That's what I put in there. And then I'm using a capacitance value of 0.1 microfarads for my capacitor. So go ahead and run that simulation and go ahead down to 3.4 here again, right? So once you go ahead and open up your 3.4 blow plot, you may see that at some point this function actually looks like a wideband filter, and it looks like it's a bandpass filter. But that's only because these are huge frequencies where the capacitance of C2 is actually so great. Sorry, the input impedance of C2 is actually so great because of the frequency here that there's some attenuation going on in the circuit. So actually what I'm going to do is on the horizontal scale, I'm just going to bring it down a little bit. So we're only actually interested in the first maybe 1 megahertz of bandwidth there. And that'll give me a nice signal that's not a bunch of junk. Actually, guys, I had multiplied my resistance values by a factor of 3, which I shouldn't have. So my resistance value actually with a capacitance of 0.1 microfarad is actually 318 ohms. So once I've done that, I can go back up here on my boat plot for 3.4, and I can look at my 3 dB cutoff frequency, right? So if I go over here, I can find a spot where this value is around 3 dB. And we can see right around 3 dB, I have 5 kilohertz, right? Which is exactly what I calculated for my particular filter here. And we can see that there's still some junk over here. So let's get rid of that by just, again, decreasing our bandwidth a little bit. And then we can go up in here and we can see this small little portion here is our passband, right? And we can see that I'm at 0 dB in my passband, which is exactly what I calculated. So I want it to be at 1 volt per volt, which in 20 log 10 is 0 dBs. So we can see my passband is at 0 dBs. So basically, what you're going to do for this section is you are going to construct the 8-line table as instructed here with these different frequencies of interest. So 300 hertz, 600 hertz, 1.2 kilohertz, 2.5 kilohertz, 5 kilohertz, 10 kilohertz, and 20 kilohertz. And you're going to put these values in a table and just put them in your lab report. And that's along with a screenshot of the actual bode plotter output from Multisim, right? So you can go ahead and screenshot that and actually fill out the table of values for your report. So I'm going to go ahead and just show you, for example, 300 hertz, where it asks for that one. When you're at 300 hertz, as long as you are somewhere in the ballpark, again, just like I said in the last lab. So 304 is fine, and we can see that my gain is at negative 24 dBs. I can go over here and also measure the phase at these angles, or sorry, at these particular frequencies of interest. So once those are plotted and you take a screenshot of the graph here, I think the last step you're going to do is actually just take 2 points of interest on the graph. So take perhaps 300 and 600 hertz would be your best 2 points because they're within that stop band, right? And you're going to compare it to the 20 dB per decade theoretical value that you should be getting for the slope. So basically take any 2 points within this sloped region here. So any points between, let's say, 10 millihertz and, I don't know, 1 kilohertz. Any of those points can be taken. And as long as you take 2 of them and do x2 or y2 minus y1 over x2 minus x1, just rise over 1 as you did in grade 9, you should be able to find the slope for that line. So once that's all done, you can go ahead down to 3.5. 3.5 is actually quite simple. Basically, you're just going to look at your pre-connected circuit. You're going to verify that you have the correct component values from your pre-lab. And then you are going to just connect a 2 kilohertz square wave to the input of the integrator and sketch the input and output waveforms. So don't sketch. Again, take a snipping shot, but same deal. So again, if your function generator isn't connected, you can go ahead, delete that for now, and I'll do Control-Shift-W, bring up my wiring command. Should be able to wire those up. Oh, that would be wrong. And I can, there we go. Okay, so once that's done, we're gonna go square wave. We want kilohertz, and we want 2 kilohertz square wave, right? Okay, so we can go ahead and hit run there. And once we're there, we can go ahead and XSC4 here, which is the scope for this channel, right? It says VOUT5 and VN5, VOUT5, VN5. So we can go ahead and move those scales up, get a better indication of what's there. So we can see that our input is a square wave, right? And our output is actually a triangular wave, right? So we can go ahead, take a screenshot of that, and note why that's happening. This is an integrator circuit, so there's a very good reason for that, but explain that in your lab book, and make sure to mention it in the report. And again, make sure you're using your calculated values from the pre-lab for C3 and R11 here, right? Because it gives you some time constraints on how fast this rise and fall for this square wave should be. So please take those into account when you're actually calculating your C3 and R11 values, because I haven't switched them from what's in the schematic. So now, last but not least, we're going to modify this low-pass filter to now, modify the integrator circuit that we just built to actually model a low-pass filter. So make sure you're calculating your RF value from your 3 dB cutoff frequency and the CF value that you've been given. So you've been given a value of 0.01 microfarads. I'm going to use 0.1 microfarads for this experiment. And I'm actually going to use a cutoff frequency of 2 kilohertz instead of 1 kilohertz like you guys were given. Okay? So make sure you're calculating your 3 dB cutoff and using angular frequency and not the frequency you're given, right? So you need it in radian per second. You need to multiply 1 kilohertz by 2 pi. So in my case, I've multiplied 2 kilohertz by 2 pi, and I've found that my resistance value is around 800 ohms. And then I can also get from this equation over here that the real part of this equation I want to equal unity, right, in the passband. So again, I'm going to do the exact same modification that I did in the last step, and I'm going to just ignore this J term and just do RF divided by RI should equal basically 1. And that insinuates that RF should practically equal what RI is. So from there, I'm going to go ahead back into the simulation tool. Go ahead and make sure you stop the simulation. Then I'm going to go in here and actually adjust my resistance values for R13 and R14, right? So as I just told you, the values that I calculated were around 800 ohms, so I'll go 795, 795. And again, I used a value of 0.1 microfarads here, but you're going to have to change that to 0.01 U for your simulations. Go ahead and run that again. And you should see the magnitude and phase as a function of frequency, right? So go ahead and increase the vertical scale so you'll just see a little bit above the 0 axis. And we'll go ahead and limit our bandwidth again. Just limit it to maybe just that region, right? Because we want this nice passband that goes up and up and up until our cutoff, and then we start to drop. So I can see my 3 dB frequency is right where I calculated it to be. So I chose 2 kilohertz here as my cutoff frequency. And yep, I can see that my negative 3 dB point is right around 2 kilohertz. And then if I go back to my passband, which is over here, we can see that the value for the gain in the passband is almost exactly 1. It is almost, well, it is 1 actually. So during most of the passband from 1 millihertz to about 15 hertz, it actually is 0. So we're having absolutely unity gain in the circuit. This is just acting as a buffer, the circuit, up until the 3 dB point of 2.12 kilohertz, and then it is attenuating all the signals above that, right? So if we went and spaced that out a little more again, we can see that there is some little blips, but again, we're going to ignore those because those are, again, when the capacitor starts doing funny things at extremely high frequencies. So basically what we're going to do here is we're going to take the same table that we created for the actual high-pass filter, and we're just going to fill in the exact same values of interest, so 300 hertz, 600 hertz, 1.2 kilohertz, and so on. And we don't need to calculate the gain of the filter in dB because this has already been done for us in the mode plotter function on Multisim. So we can actually just go and look at the points of interest and actually get the value for V out over V in at each of those particular frequencies of interest. So go ahead and do that, and take a screenshot of this actual plot, right? Because this is the mode plot. This is the frequency versus gain, which is V out versus over V in. So take a screenshot of this, include that in your report. Maybe include a screenshot of the phase if you'd like. It never hurts. And then the last but not least, again, grab 2 points of interest along this line. So let's say it has to be somewhere within this small little region here. So let's say in my case it would be around 3.93, so 4 kilohertz to, let's say, 1.5 kilohertz. No, a little more than that. You want to be a little past your 3 dB point. So go back here. We can see that the slope, so I'd say about 65 kilohertz to 6 kilohertz would be a good range, and you could take y2 minus y1 over x2 minus x1, and you'd actually get a value for the slope of that line there in the attenuation band. So last but not least, it asks us to again attach the function generator instead, right? So we'll go ahead and we'll just delete this component for now. Make sure your simulation's stopped. And go ahead and wire up the function generator. Once you have that wired, you can go ahead, switch it to a 1 kilohertz square wave, right? And once that's done, go ahead and hit run once again. And you can look at the output and input waveforms, right? So if we go ahead and decrease the volts per division there, you can see there's some clipping going on. But basically what this is aiming to do is get back to a sinusoidal wave, right? But it's going to act more like a sawtooth, as we saw in the previous section, right? But what are these little ramping and deramping stages? That's actually the capacitor's charging and discharging cycles, right? So you see that small little curve. You talked about that in 2501, and you can calculate that based off the RC constant. So once all that is done, that's the software portion of this lab, and good luck. And we'll see you again for the hardware portion, where we'll go through some new function generator stuff that you guys haven't done in 2501, and we'll also get you to re-perform the summing amplifier in the lab in an actual hardware measurement. So good luck for this part, and we'll talk to you guys soon. Bye-bye.